and worked during around 15 years as a computer scientist in very competitive and big companies. On the project and big project, now I have the habit to erase the board. The teacher habit. I like a clean board when I present myself. Yes, I divide my presentation in 3 parts. The first one is simulator. Jacob introduced. It's more a mathematical approach I've done. If you are interested, I put the mathematics with you because I'm a mathematics teacher. It's my I have no problem with turn me around. First, I leave my slides. Yes. Then, what's on right in my computer? I'm not familiar with because I like to make my course with the chart and board, not with the slides. But I ask you to be intelligent with me. Yes. For my verification, we started 2010. Very, very simple history. Because I prepared the code Jacob used. It's a toy. The different part. It's a toy I give to the community to make experiments about verification. You have seen in the code, there are always bugs. I think bugs is a good way to experiment and I provide the code because the simulator I've written is, in my point of view, complex enough, but also funny enough. You know, I understand why Jacob liked it. Because it's a physician, it's a doctor in physics. It's a dynamic system, it's military in physics system. It's for me, it's quite funny. And if you are, I have another part, it's very theoretical. It's the theoretic basis of the formal verification, the R logic. Where is confident with this logic? We know the R logic. One youngster. One is very good. I'm very jealous for the next presentation because I use very, very much people. And I think you are more interested by my presentation. If you are not, you are already interested by theory. I put investigate in the part, but I prepare for you more practical exercise with the tool provided by Editor to understand what is what are these formal verification. Okay? Starting with what is the formal verification. It's a very basic presentation. Formal verification is simply the proof, the act of proving or disproving the correctness of an implemented algorithm with respect of given formal property and using formal method of logic. It's not mathematics, it's logic. It's the same for me. Yes, it is a simulator. It is a physical, it simulates the physical world, sand falling on the ground, forming a pile, and sometimes there are avalanche, there are events like avalanche, and the grain fall on the pile. It's interesting for example, simulate effects, for example, the avalanche in the mountain, for example, but also a bubble crush in infinite form, example. The race, I find two types of race, two kinds of race. You want to race, you have a sign here. Each, it's you must make an array. Sorry, an array. 18 on 18 by 18. Each place it's empty or set up by grade. For example, space is empty. Space is confined, set up by grade. The green is time t for plus 1, and time t. There are two green green ray. And the right one would occupy the left or the right place because it's empty. It would occupy the space or the space. Because there are enough grain on it. The pressure on this grain, it's enough to push it laterally. Understand? And here it shows to go at the right for us. Okay? It's one kind of race. Second kind, the blue wine. The blue wine is the 2-1 race. The two grain would like occupy one empty set. They are raised between these two grains. Okay? It's understandable. Well, there are a lot of formalism. This is quite interesting, like this example. Say a tomato is defined by rules. And rules is useful, it's easy to be formalized in terms of precondition, post-condition assertion. The purview of the system is defined by rules. For example, here, this grain could fall because the cell then this one, this configuration. Each case is defined like this way. For example, the right move. The side can have the priority, and for a lateral move toward the right place, we need to have two empty cells to move. It's a lot of rules think it is interesting to make exercise in the time of proof. Those rules is those rules. Yes. No. So automatic aspect use for this relator. Code. You are familiar now with this code. I'll go in next to show. No, I think no. Plus, I conclude with my code. My code is written for you to make exercise. Every put on the internet, you will be free to use it. And your feedback is welcome. Now, the theory of verification, formal verification. Begin with lettering. It's sure, it's the deepest. It made a first proof at the end of 15. But it is a little paper. It's not known paper, not no job. The first approach in this way is done by Freud in the end of 60s. He used an logical assertion to make a proof on the flowchart. But this is not a system of proving. It's practically like this. It's a suspicion proof. So it's our the first paper about formal verification is done by R. He said a logical system will improve with inference root, but it's not complete. It's the extra complete 5 years later. And with the extra, with the computation with the extra, we're able now to prove the correctness of the program. It is due of the R logic. In certain case, it isn't. It is impossible to prove infinitely the ending of the program with the extra. I think it's possible to prove the ending of the program. It's a very lot of formula. What is important to consider? I propose to you to come back at the first year of your studies to remember that a program may act on the data. The purpose of the program is to modify the data. And then there are two aspects of the program. You have the computational aspect and the data aspect. And it's important to consider how the data change with a particular statement. And now, for this purpose, we need to define our language, like data, be formal computation, like a very simple language. Only set a few identified formal language, like imperative language, like data. The language I use to modify the content of the data, the system. It's an expression like a number, variable, or more complex construction with operation. And I propose some statements. Still, we do nothing. Assignment, composition, if structure, and loop structure. Very simple language. With this construction, we're able to explain the logic of the R logic. But syntax is not enough. We need to understand how the language, the imperative language, modifies the data. because the modification of data is we need to control when we make a proof. We need to understand how the data of the state of the system vary. The kernel is the heart of the program. Is how the statement change the data of state. So we need the semantics to understand how the statements change the data of state. And we need simply to evaluate the expression, and we need to know all the states. The sigma is the complete set of data, complete set of variables, and a series of instructions, S. And when we execute the next instruction in the sequence of instruction, the data, the whole data is changed in sigma code, and it remains. We remove the executed instruction, the executed statement. Okay? If you execute more than one statement, we use simply the star, which means we use a lot of statements for which the state, the value of the variable, and it remains some instruction, some statements. And the program is terminating execution when we reach skip statement. Okay? Then we have no syntax and semantics to know how to represent how to manage the way of the data change regarding to the statements. For this we need the first order logic, logic of predicates. We make with this logic the conditions, verification condition, like the condition, post condition, the condition like invariant loop variant, sorry, loop variant, for example. This is the predicates. Defined with this syntax. The predicate is a function, a logical function. It's not complex. Semantics is the same approach than the imperative language. We need to evaluate if a predicate is valid or not. It's a formula, a logical formula is true or not, is valid or not. We can use the expression of our imperative language. For example, x is greater than for example, in either. For example, e there could be x greater or equal to 0, for example. It's an expression written with our imperative language. Why not? We need this one to create the first condition, for example, the verification condition. And we could make logical computation with and or not implication, for example. And the same for the we need to say if a predicate is valid for a given state. It's finished? Okay, cool. I go more. Yes, with this logic, we could create a logic, our logic. We must state the triplet, our triplet. It is the precondition before, must be checked before the execution of the statements, and the post condition Q must be satisfied the data. And the post condition. The S must be the resulting state. And the resulting state must be satisfied post condition Q. It's clear? From this, the rules how I give to us, for example, the precondition is the same as the post condition when we do loosely. When we make an assignment, the post condition, we need to test, to check if we are able to perform the assignment in the precondition state, and the assignment is distinct state, the post condition. For example, here we add 1 to x, y is 23, and we need to check if x more y is equal to 23. Sorry, I terminate, sorry. If you are interested by this logic, I respond to your questions. Can I terminate?
I'm sorry, my remark is, could you please have your presentation?
Yes. Oh, sorry, 4 minutes.
1 minute. -4.
-4, sorry. Yes. Yes. Look, the tool is used to make proof in the analytical provided by editor is net proof. Is the tool provided? This tool can generate files in the Y3 platform. This platform, it's a platform used to make proof in using the mathematical prover, theorem prover. And it is the link. That proof is a tool making the link between your code in the data or the whole language used by Y3. And Y3 use the mathematical prover to make the proof. It is provided by when we install the other 2005. You need to install the package Start Highlight GPL 2013. You need the net proof tool. It means when we revoke the tool, you are access at the check made by the prover. The checks are in the code with the precondition, post condition, the loop invariant, the loop example. But you can check which checks are loaned by the tool. We have the list of the checks. It's interesting to, here I have only the face of the tool, but you have here a check of the device diagram. control how the tool works. Thank you for your attention. I hope I have a lot of things to tell you, and I hope you enjoy my presentation. Do you have questions? Any question? It is so difficult or so simple. I hope it's the second option.